UT, puis
Postdoc. En France, c'était où?
c'était à Brest. C'était à San Francisco, à Brest.
San Francisco. Joint postdoc.
Ça part du...
Le Sherbrooke pendant quelques années.
Ouais. C'est pas là. Sherbrooke 2020-2025.
Attends, j'ai présenté.
Pas aussi, on dirait.
Est-ce que?
Il part pas de là. Ok, il est parti. C'est bon. Ok.
So I think we're ready to get started. Good afternoon, everybody. I hope you're doing well. I hope you can hear us well online. If you can give us a little sign, that would be helpful. We are here today for our first noon talk of February 2026 in the 2025-2026 series of the Medical Physics Unit. Our speaker today is one of ours and has been one of ours off and on for a relatively long time. I'm happy to present Professor Martin Vallières. Martin was a master's and PhD student here at McGill already when I was just getting started on teaching, and we collaborated on some work back then. Martin completed his PhD under the direction of Issam El Naka in studying radiomics. And at the time, radiomics was, well, I don't want to say in its infancy, but it was sort of in its early popularity phase. And since then, Martin has spent some time in France and in San Francisco, both for postdocs, working with the world leaders in radiomics research, has established some international collaborations and projects in this area. After his postdoc, Martin was hired at the University of Sherbrooke here in Quebec under a CFAR chair, and he established a lab there called Medomics. And after some time in Sherbrooke, we were fortunate enough, or maybe lucky enough, or maybe sly enough to lure him back to McGill, and he has recently joined the faculty here in the Medical Physics Unit. He is an investigator at both the RIMUHC and the Lady Davis Research Institute of the Jewish General Hospital. Teaches in our program, or soon will be teaching in our program. Already has, he is teaching in our program and already has his lab starting to get set up and already set up here at the Glen site. So it is my pleasure to welcome Martin Vallières to speak to us today for the noon seminar.
Thank you very much, Yves. Thanks for the introduction. Very nice introduction. Thank you. I'm glad to, as he said, I'm glad to be back. Glad to be back now. So it's been 5 years in the making, let's say, that I had in mind to one day maybe come back here, and now it's done. I am back at the MPU, and I'm glad of it. So the presentation I'm going to do today and research program obviously was started and built on my first professor appointment in Sherbrooke, and now I'm transferring back here and trying to obviously will adapt it a little bit more to medical physics. So I'm glad to present that to you today. The title of the talk is Integrative Modeling of Heterogeneous Data in Medicine. I'll try to explain a bit more what this means throughout the talk. So my research laboratory, is Medomics Lab, right? The overarching goal is to try to contribute with our research to better precision medicine. I like to bring always this quote from President Obama in 2015 to define precision medicine, right? Delivering the right treatment at the right time, every time to the right person. Trying to contribute to this. And just to give a rough idea of different topics that compose the lab consisting that forms Medomics Lab. Here it is. You'll see again the slide at the end. Actually, I'll put the faces of the different members where they contribute in this diagram. But 3 main topics, let's say: AI for health, so artificial intelligence for health, so modeling, building different methods, and thinking about deployment of those models, those methods that we develop, more specifically in terms of graph neural networks, multimodality modeling, federated learning, model evaluations. I'll go through a couple of these in the next slides today. So that's the first circle here. The other one, medical image analysis. So as Yves mentioned, my initial research started in radiomics, quantitative image analysis, machine learning associated to it. So it's still actual in my research program. Software engineering, more and more we're developing different interfaces to be in better synergy with clinical researchers, actually try to build different environments, working environments with clinical researchers, have a better synergy between these interfaces and the backend code that we develop inside a platform that we call Medomics. This platform is at the center of it all. The different research developments, we try to integrate it into this platform. So there's Medomics Lab, but there's the Medomics platform. It's not that much original, but it kind of shows that the developments of the research laboratory are meant to be integrated into this platform, and I'll present it today. And in the intersections, there are, let's say, some different sub-packages, interfaces also developed along the way that are also integrated into the Medomics platform. I'll touch upon one in particular today, Med3PA. There's MedFL, MedIML also. So we'll have the chance later, I hope, to later in our lives together here to discuss more about all of this. So this presentation really towards integrative modeling of heterogeneous data for precision medicine. Just want to give, again, like maybe a big picture of where this all fits into perhaps a long-term research agenda, vision in life. In my current program, I focus, let's say, on at the center here on what I call specialist AI, which is more about predictive modeling and building specialized models for specialized medical domains like oncology. Obviously, we've heard much about what is more called generalist AI with the different types of foundation models and generative AI. Precision AI also is something that needs to be integrated into this whole realm here, where causality is involved in order to go towards more personalized care. So go towards more continual causal learning. So this is all part of the plan, let's say. I think this nowadays we can think that this can be really well bridged with developments in agentic AI. So that's the big picture, but today I'll focus really on this part of the developments of my lab. So you'll hear about three parts today in terms of, again, predictive modeling, specialized medical domains, integrative modeling, basically. You'll hear about prediction, validation, optimization, and I'll explain what this all means. Let's start with that first part. Example of predictive modeling. I just want to put here the general causal graph of life, basically, where in medicine, where you could have patient state, features X, patient present at the hospital. Obviously, this will influence the treatment that patient will receive and the outcomes associated to it. Here are the basic relations between state of a patient, the treatment that person receives, and the outcomes, basically. In predictive modeling, in what I'm going to show, we basically really concentrate on these relations and do not necessarily take into account these relations here. And it's a huge assumption, a huge but reasonable assumption, which is that all patients basically receive the best possible treatment according to their state X, right? And the involvement of those relations would involve also causal learning, causality, which could be discussed in another talk later on. So predictive modeling, basically building a function F that maps a set of features, a state of a patient at a given time X to an outcome Y. So the goal is really to develop that function F, which provides the probability of observing, sorry, I'm going to move that around, of observing outcome Y given a state X of a patient, with the rationale that this should improve our assessment of patient X, of patient state X, give more information to the clinical teams to, we hope, help in personalizing treatments. Here's an example of one study that I did here at the MPU, which an example of one type of predictive modeling study that could be done in oncology. In 2015, we developed a model to predict as early as when patients presented to the hospital, predicting lung metastases, the likelihood of developing lung metastases in soft tissue sarcomas based on different types of modalities of data types. So what is X in that case, or what was X, or what could be X in that case, the different types of data? We mainly analyzed images, MRI images, so extracted quantitative imaging features out of that. But we could also have integrated different types of text reports that could have provided complementary information, perhaps. Patients could have, we could have accessed to multi-omics profiles, demographics information. So my point here is that there's different types of data that are available at a given time point, which are pretty different in some sense, that we need to model and that we need to take into account differently. The idea is of the integrative modeling framework that I'm going to present is how to combine these different types of data together. So this is multimodal data, right? And what I'm going to present today, actually, I prefer to say that it's actually really heterogeneous data in terms of predictive modeling. They really have to be considered differently into the predictive models. So based on these different types of information, for example, how do we use all of this and combine that efficiently in a predictive model to build a function f? The core algorithm that we use to do this is the graph neural network. And I will not go too much into details here, but basically, we have a good idea of what is a neural network, but a graph neural network actually allows you to include also relationships, different relations between the inputs, and at the hidden layer levels as well. Overall, with graph neural network, you combine the power of neural networks with the power of relational inference of graph models. So this type of algorithm is useful to exploit useful relations between variables, between the different types of data that I've just showed, and patients, because you may want to base your prediction based on, you may want to help the predictions of a given patient based on the predictions of other patients that have similar care trajectories, for example. So you can model these relations with graph neural networks between variables, between patients. So here's just a quick example of a two-level graph. Patient connections, feature connections, and when you put it all together, basically it becomes a two-level graph to do the prediction for a given patient. That's basically the usefulness of graph neural networks in that framework. And here is an example of a beautiful, actually, graph neural network framework architecture. The idea is not to go into details here, but the point is that this paper, published in 2023, and this architecture actually is really beautiful in the sense that it allows you to model many different types of relations between patients, between variables of different patients. All the different types of relations can be included into that framework. So it's great. It's difficult to scale though, but that's one disadvantage, but it's a beautiful type of fusion of multimodality data. So it's a beautiful model-driven fusion of multimodal data that I call, but not necessarily what I would call a data-driven fusion, and not necessarily considering data as heterogeneous in the sense that there could be different levels at which different types of data could be fused or taken into account in the overall fusion process. And I'll try to explain this here with this vision that we have and that we're building currently. is to build a mixed data and model-driven fusion of heterogeneous data. What does that mean? The idea is to take into account, yes, okay, you can do multimodality fusion like I've just showed in the last slide, fusion of different data types into a given predictive model to build your beautiful function F that maps all those different types of multimodal data X to an outcome Y. Okay, good. Medical data is multimodal. It's also hierarchical. And that's a word I'll always have trouble to say, sorry. Hierarchical. It's acquired at different biological scales. Here, scales are represented, for example, in terms of the biological scale at which it's acquired. You could think of this lower scale could be multi-omics in general. There's features that could be extracted here that represent the anatomy. And here, some tabular data, hospital data that would characterize patients more in their global state. So there's different biological scales at which data is acquired or what it represents actually. So let's take that into account actually into modeling, in doing what we call integrative modeling. So modeling that hierarchical nature of multimodal medical data when learning patient representations for predictive modeling. So the idea is to have that hierarchy here. Now, as I previously said, also there's different relations between these different types of data, different relations between multi-omics profile and the anatomical features that you're gonna characterize afterwards with medical imaging. So there's different interactions between the different types of features at the different levels. Some of them we know, some of them we don't know. And that's where what we're trying to build also is a reinforcement learning framework to discover those useful cross-modality interactions that could be useful for predictive modeling. Okay, so these cross-modality interactions are represented by these blue arrows here. So this overall workflow, basically I'm getting at the end of part one. This overall workflow, I'll try to do a schematic here a bit. First, you have to define a hierarchy. You can learn that hierarchy if you don't know it a priori, or you can define it. Here, we could say, okay, it makes sense to put, for a given predictive problem, to put these types of data, multi-omics followed by anatomical features, followed by demographics features. Would make sense to put it in that order, but it depends on the problem. You can actually learn it or define it or make that in a hybrid mode. So first you have an hierarchy. So there's that lower scale here type of features. Let's say we call it scale X. It's actually written scale X, okay? The idea is there's different also useful multimodality fusion algorithm, like I've just shown before, that can allow you to extract initial embeddings from here, initial feature representation from those different types of scales. So in this idea here, it's not about reinventing the wheel on extracting the best quantitative imaging features there exist, or the best multi-omics quantitative imaging features. There exists plenty of different multimodal model fusion that do that. So we can actually exploit, these expert analyses that already exist, build also our own, obviously here, to get an initial vector representation of all those scales. The idea then is to combine these vector representations at the different scales in a smarter way, in an integrated way. So, expert analyses, just to go back on these expert analyses, and I'm giving examples which dates to a couple of years, but that could still be useful also nowadays to get these initial vector embeddings. Obviously, there's other research that has been done in terms of For example, this is to extract quantitative imaging features from medical images, a dense net. You can use a pre-trained dense net to get vector embeddings. For clinical text, and that dates to 2019, it's like the old version of analyzing medical notes here with pre-trained clinical BERT, but it can still be useful to get extract embeddings from clinical notes. Of course, you can use more sophisticated architecture to get your initial embeddings for text, but that's just an example that can still be useful. So these are examples of expert analyses. Now, how to combine all of this together? The idea is to go in a hierarchical way. First, there's different embeddings for the different, so vector representations for the different subtypes at a given scale, which are represented by the different colors. It could be genomics here, proteomics, whatever. Could be different types of sub-data types, could be different sub-data types here at this level. So there exists already algorithms that you could use in an expert fusion way to combine all of this in a smarter way than in a smart way. For example, this is an expert fusion algorithm for multi-omics data. So not just take into account RNA-seq, for example, but other types of multi-omics data. And so you can use at this level these types of multi-omics expert fusion to continue the cascade of integrative modeling. That's an example of an expert fusion that could be done at this point. That's another example of a really model-driven fusion, not necessarily built for multi-omics data, but in a more general way. This pool dates back to, again, 2018, but can be used as a type of fusion that you can choose, basically, that you can select in this scale X representation. Then you can start combining scale X representation. Then you can start combining it with the raw data at scale Y, which is at a higher level scale. Get that scale Y representation, which is basically a mix of the raw or almost raw embeddings here from scale Y, but combined with that scale X representation from the expert fusion at that scale. So I think you get the point. You get basically a cascade of different fusion up to the highest level scale here, Z, which would represent the global state of a patient, or features that represent the global state of patients. So by doing this cascade, we're trying to show that we're going to get an enriched patient representation to enhance predictive modeling. That's basically the workflow of integrative modeling that we're trying to build. Plus, in there, as I previously mentioned, you can also add those arrows here. I'm going to put them again. Those arrows that you could discover that would basically enrich the initial vector embeddings right at the very start, because the interactions between the different features at the different scales basically allows you to extract quantitative imaging features that take into account the interactions between the different scales. So you can add, on top of this, you can add those arrows to, most likely, we hope, get an even more enriched patient representation. That's the workflow of integrative modeling. So in summary for this part, this data-driven hierarchical modeling via cascade of expert model-driven fusions, that's what we're trying to build. Is it going to lead to improved performance? Maybe. Is it going to lead to improved interpretability? We hope so too. And we were trying to work hard to make this work in a hybrid mode where clinical expertise, different expertise can input different expertise into that to define that hierarchy, or already cross-model interactions that you would already know before starting the initial process. Okay. That was part one. A bit kind of rough modeling, or we think better modeling of multimodal heterogeneous data, so towards integrative modeling. Part 2 is about to validate these models, better validate these models, because you have one model, yes, your whole plan is to help clinical researcher, is to help the clinical workflow, basically, to have this model deployed in real life to help patients. Well, so another big part of all this research program, basically, is to develop methods to continuously evaluate those predictive models per patient profiles. In the sense that, okay, a model exists. Let's say last week we've just built that model and we're trying to, or we built that model here at McGill, and we're trying to see, okay, can we deploy it in another hospital in Montreal or another hospital in Quebec? So we'll have to do some assessment of its performance in different institutions. So that model exists. So you would say, okay, I'm going to go and deploy that model in Sherbrooke. Well, we would get a data set and evaluate this model on a given data set present at Sherbrooke and say, okay, it works well in Sherbrooke, for example. That's very good. What we would usually do is get a global performance assessment of that model in another institution. What we usually do is that we get a general performance metric. That's the evaluation, let's say, in another institution. Okay, good. An AUC of 0.9 in the other institution. We're happy. We think that it fits well with the type of global evaluation that we had when we built the model, for example, here at McGill. So we could say, okay, good, it's good for deployment. The idea is to develop methods to continuously decorticate this performance metric, which is right there, because it's the performance on the global set, right? So is there differences in performance across age, across male and females in this other institution? Basically, that's just a toy example, but this AUC on the global sample at the other institution, 100 patients, for example, if you break it down, perhaps you would discover, okay, so basically, yes, globally, we have a good performance metric of 0.9, but in females, basically, the performance is 0.7. In males, it's 0.95. Okay, so what does that mean? And then you can break it down again even more in terms of age, for example. And these are just examples of how to create those different patient profiles. Okay. Yes, you have the global evaluation. If you break it down into different profile, like shown here, profile BC basically is older males, and profile BD here is younger males. So we want to break down the performance across different patient subgroups to detect performance shifts, biases, so per patient profiles. So that's one thing. Detecting those biases, yes. Those breaking down the evaluation of performance at a given time point, let's say tomorrow in the other institution, but also we need to do that continuously. We need to do that over time to detect perhaps data shifts that could occur in a given institution. And this type of predictive, we called it predictive performance precision analysis in medicine, so MED through PA, to this breaking down and continuous evaluation of predictive models. We called it, we've created a sub-package to be able to do that, which we call MED through PA, which is integrated into the Menomics platform as well. So the idea, basically, of MED through PA and of this part 2 and continuous evaluation is to basically be able to detect when these models, when AI should say no. So just an illustration here. What would it mean? You trained something on one institution. Good, you have scatter plots of two-dimensional data, class 0 in blue, class 1 right here. Here's a model, good. simple model that differentiates between the two classes. Now you arrive at the other institution and you're in perhaps multi-dimensional space. You don't necessarily detect those different clouds of points or different profiles of points here for which the model maybe should not be applied. Maybe you should not apply the model on these different types of data points in another institution that you need to discover actually before deploying. That's the idea here. That's the basic idea of MetroPA. And here's again with this scatter points, this plot of points here, these same points here. Basically, what we're trying to do is define those regions for which the predictive, for which we have a higher confidence in prediction, So we would say, okay, these regions here, this new cloud of points basically would this new cloud of points would relate to the profiles. We try to make it relate to those profiles that has lower performance. And that would be most uncertain compared to the others, to the other regions. So we build these regions in high dimensional space, basically. That what it comes down to is building basically that tree of different profiles. So we learn the predictive confidence. That's the idea of MetroPA. Learn the predictive confidence to provide a predictive confidence on an individual basis per point, but also aggregated by, for example, patient profiles like here. So aggregated by patient profiles, so creating those regions basically here. That's the idea. And here, the idea is that if you remove most uncertain points or least confident points, if you don't use them, these points, let's say in an evaluation set, you expect that if you start from the right here and you remove those points here that have least confidence, you expect that your performance will increase. The overall performance of your model. So that's basically the idea, and the idea also is to have clinical teams select some type of threshold based on predictive confidence for model deployment, on which they are confident that, okay, if we use it at 90%, for example, there's 10% of patients for which we will not use the model, then we're confident that we have sufficient performance for the rest of the 90% of patients for which we apply the model. That's the idea. So the intended use of MetroPA, here's an example with two institutions. You have an institution A, we build a model here, good. We could attempt to deploy it in a new institution, in Sherbrooke, for example, good. What I've been saying is that, okay, to apply the model, deploy the model, usually we use model prediction, right? We say, okay, here's the model, I have new patients, I pass it in inference into the model spits out a probability of a certain outcome given the patient state X. So we use that prediction model by hoping to personalize treatments. What we're saying here is that MetroPA could help in doing better internal validation, temporal validation of those models, external validations into a new institution. So doing this internal validation in the same institution at which it was trained, continuously validating it in a temporal manner, and also obviously validating the performance in new institution, so that when we deploy it, we don't just use the model prediction, but we also provide the predictive confidence, the tree of profiles for which the predictive confidence may be higher or less. The reference MDR curves that I just showed actually here that I did not explain that much, but that basically gives you an idea about the percentage of patients for which you could not apply the model and how it would relate to a better performance in the remaining global data set. So the idea is to provide more tools at deployment to the clinical teams with this technique. And we've applied this model, this technique, sorry, to a real world scenario, real world example. Okay, in Sherbrooke in the last years, predict the hospital 1 year mortality risk, something done in the literature, let's say since 2014. The idea is to with this type of model is to be able to allow the clinical team to initiate goals of care discussion earlier. And this hospital 1 year mortality risk is really like a general type of model, not necessarily applied to oncology specifically, but really a general type of model that uses all the different types of, but not all, but a lot of different admission data types that you get when a patient arrives at the hospital in different departments. So in this type of scenario here, we have applied MedRPA on 123,000 patients in Sherbrooke. So the idea was to learn the predictive confidence, get this type of curve that shows, and it's really tiny here, but let's say you have a declaration rate or a threshold that you put at 95%. You're confident that, okay, for those 5% of patients defined by the predictive confidence, you're confident that you're more confident that if you don't apply it on these 5% of patients, then the rest of the 95% of the patients with which you would apply this, for which you would apply this model, you have a better confidence that your performance basically of your model would be higher. So we can provide also this type of tree by profiles. So this is a tree by profiles by different types of variables. Basically, that shows you performance, predictive confidence by profiles. To basically define, basically as an example of clinical use, define profiles, patient profiles, for which you should reject the prediction of the model. Profiles for which you can be more confident that you can apply the model, and regions for which, patient profiles for which you should be more careful in applying the model, basically alerting clinical team, put in an alert or a flag or something to say this patient before, these group of patients before applying the model shouldn't do a little bit more investigations. That was the idea of part 2 of this MedRPA technique, open source, available on PyPy. You can have a look at it. There's currently an article on medRxiv that describes this. And this is the title. So MedRPA part 1, we plan to do different parts basically to this whole technique. The next parts will be more about providing even better explanations of the different types of uncertainties in this tree of profiles, and trying to correct actually these uncertainties when you retrain the model. And this is all part of Medomix, the final part of this talk, and the center in the Venn diagram, basically the platform in which we aggregate all those research developments, basically where we try to aggregate all those research developments. MedRPA is part of Medomix, and Medomix basically is the center, yes, of this part 3 that I call optimization, and not optimization in terms of machine learning, but optimization in terms of how we work together as interdisciplinary research teams. So we believe that this platform should allow better synergy of medical AI interdisciplinary research teams, so optimize the way we work. Here it is. It's a unified analysis platform for clinical researchers and computer scientists in order to optimize basically the working synergy of the last 2 parts that I presented, modeling, evaluation, into a unified analysis platform. So the idea is to go from, let's say, from a traditional, more sequential process, let's say, and it's really a view of the mind here where computer scientists do AI computing, go back to the clinical team to show the results, and go back to fine tune with the computer scientist that adapts the code, and more of a sequential process where maybe we could be in a state where we work more in synergy inside the platform altogether to do data management, AI hypothesis, AI computing, results visualization into this integrated platform. So that's the idea of the design of this Medomics platform. And again, maybe some of you have seen it. I have this video to show you that will give you a 2-minute a quick overview of what is Medomics. Here it is.
Despite their essential role as experts, clinical researchers face challenges in accessing essential tools and collaborative channels to use AI more effectively. Bridging this gap requires empowering researchers with resources to drive AI advancements and fostering more collaboration between medical and computational fields. Medomics is an open-source platform designed to support the research community and help medical AI teams to better work together. It addresses these challenges by, first, providing clinical researchers with easy access to AI tools, enabling them to independently run their own experiments. Second, by facilitating collaboration among interdisciplinary research teams, bridging clinical expertise and computational science. And third, by offering computer scientists an integrated environment with access to multiple state-of-the-art solutions. The Medomics platform combines the power of multimodality medical data and a collaborative research environment to drive innovation in personalized healthcare. It empowers teams to develop predictive models for personalized treatments. The Medomics platform offers versatile usage levels, from user-friendly built-in pipelines to highly customizable Python libraries, making it accessible to both clinicians and computer scientists. Its 3 core layers, design, development, and deployment, enable heterogeneous medical data integration, feature extraction, and model training and evaluation, all while supporting decentralized model validation, crucial for secure, collaborative research. Furthermore, the code generation feature is a highlight of the Medomics platform, allowing users to automatically generate Python code from graphical pipelines, creating a powerful synergy between the medical and computational fields. Accessible on multiple operating systems, with comprehensive documentation and an active community, Medomics is ready to support your journey in medical AI. Visit our website to get started and join a community dedicated to transforming personalized medicine through integrative data modeling.
All right. So basically, that's a workflow. Okay, that was the overview of Medomics. That's the workflow. There's a design layer, a development layer, a deployment layer. So exploratory module, input module to deal with different types of data. A big development layer where you can do machine learning, when you can evaluate models with MedTruPE, for example. We're building tools to do to simulate federated learning and do it also in the real world. And an application model so that you can really better collaborate with different researchers around the world, share models like this, and work in a common integrated environment, basically. So more info, obviously, on the website of Medomics, medomics.app. If you want to have a better idea of what's under the hood, the front end is built on Electron, Next.js, and React. The backend is basically in Python, right? So from the graphical pipelines that you build with the interface, you can generate the Python code that is run in the backend. So this all together creates the high-level architecture of the main framework of Medomics. Know also that we're currently dividing this application in 2 parts to be able to work remotely with Medomics. So installing a Medomics server in some place and being with your laptop at home, basically, to not have to transport data on your laptop. Right now, you can have your laptop and the full application, but you need to have the data on your laptop, for example. But what we're trying to build is, okay, I just have the small client on my laptop running the Medomics server in the hospital, for example. So that's the separation of the Medomics application that we're doing right now. You can visit our GitHub repository. Our project board is there. You can see what we're doing right now. We have this Gitbook documentation with tutorials, demos, a YouTube channel with all those tutorials, a Discord server where you can come to ask questions. The main website is medomics.app. So that's what I discussed today. Prediction, validation, and optimization of doing all this basically inside the Medomix platform. And this is all possible thank you to many people in over the years that I've supervised and I've worked with. There's also different research professionals that were just dedicated to building the Medomix platform, but there are also research associated to building the Medomix platform inside software engineering programs, actually at a master's level in Sherbrooke. So that helped quite a lot. So right now, my lab, right, is divided between students that I still have in Sherbrooke and new students at McGill, and here they are. So thanks to those students that continue to work hard in this realm of applications here, this realm of developments, actually. Thanks to those students in Sherbrooke, thanks to the new students, Juan, that you probably already know, Maddie, that just arrived, that is at the back right there, and the person for which I put actually 2 arrows, like an arrow because he's a master in Radiomix and a master also of software engineering now in the Medomix platform. So thank you to all of these students here. Thank you very much also to you for your attention.
Questions for our speaker? Big questions online as well. Perhaps I can get us started, and then I might be drumming up some questions. This is a less directly about your work, but related to something I saw earlier this week. An article came out in a journal in Nature, one of the Nature journals, where large language model chatbot, one or many of them, had been evaluated as like a medical information assistant and had been shown to perform sort of moderately well to poorly. But it's not the article in particular that I'm going to ask you to comment on, but a comment I saw about that said that was pointing at this article and saying this shows up as a failure of peer review, in that in the time the work had been done and submitted for peer review and had been through peer review and now had been published, there was sort of an 8 or 9 month period. Some of these journals, there's like negotiations at the beginning, et cetera. And so the comment was being made that by the time the paper was published, the work was obsolete, right? That versions of models that had been used in this work were already easily outperformed by currently available tools.
Okay.
And so I wonder, I mean, what you spoke to us about today, I think fits more in the personalized medicine end, less in the generalist AI end. But I wonder if you could comment, given that you're at least orbiting around these fields, comment on the reality that if you're using some of these tools, and by the time studies are done or enough clinical data are available to run the actual tests and publish, if we're already outdated.
Yeah.
I can keep chatting until you.
Yeah. Until I jump in. Okay. But it's the realization that I have that keeps me from sleeping at night. Sometimes, no, I'm kidding. But can we really keep pace on generalist AI? Or because right now it's really being driven by big techs, big companies, right? So it's a bit worrisome that this happens, that we don't have the resources to compete. We cannot go as fast as these. I think what we can do is, evaluate, find ways to use it first in our hospital, if it's open source, evaluate, like that article probably did, but combine it with, and that's the point here, combine it with specialties, special things that we're doing here, specialized domains. Building the next big foundation model in medicine and oncology is very difficult. So I think it's a long-term vision that someone can, and then people need to try to do it, researchers, I mean, need to try to do it as well.
Mm.
But I guess it's something difficult. I think in our role here, but how I see my role is really to make the link between generalist AI and specialist AI. So yes, be some sort in a way where I use those big text developments to feed what we're doing here, basically. Right. Yeah. Thank
Any other
you.
questions online or, oh, Yulia has a question?
Being fairly more like a philosophy question, I guess, is the concept of the confidence or the around selective clean